Okay, everyone, we are now at case 3, conjugate complex roots. Okay, so if we have conjugate complex roots, then our m1 and m2 will be of this format. So m1 will be equal to alpha plus I beta, and m2 will be alpha minus I beta. Okay, so this will be the format of our roots. So technically speaking, these are two distinct roots, right? So these are not repeated roots. So we can use the general solution for case 1, right? So y, that will be, let's rewrite that, c1 e raised to m1x plus c2 e raised to m2x. So if we plug this m1 here and this m2 right here, we will get y is equal to c1 e raised to, so what's this, alpha plus I beta x, and then plus c2 e raised to alpha minus I beta x. So that's it, right? So this is our, so this is already a general solution, but we would rather prefer that there are no complex components. So this is a complex exponential, so it is preferred that we get a real function rather than a complex exponential. So we are going to use a very famous mathematical result called the Euler's formula. So what does the Euler's formula say? So Euler's formula is e raised to um, ix is equal to cosine of x plus I sine of x. Okay, so so where x here is any real number. Okay, so let us rewrite this equation right here so that we can use the Euler's formula. So we can rewrite this as c1 multiplied by e alpha x, right, and multiplied by e I beta x. So the same thing goes for c2. We have here alpha x multiplied by e raised to I beta x. So we can now use the Euler's formula for these two right here, right? Oh, this should be negative. This should be negative. Okay, so there you have it. Okay, so let's apply the Euler's formula to that. Okay, so we can then rewrite this as y is equal to c1 e raised to alpha x multiplied by cosine beta x, right, plus I sine beta x, then plus c2 e raised to alpha x multiplied by cosine negative beta x, and then plus I sine negative beta x. Okay, so let's simplify this a little bit here. So if we recall our trigonometric identities, we know that a cosine of negative theta is equal to theta because cosine is an even function. And for sine negative theta is equal to negative sine theta because sine is an odd function. So you can rewrite this as cosine of beta x. I mean, this is not theta, I'm sorry. So this is equal to cosine theta. So this is cosine beta x, and this will become negative sine of beta x right there. Okay, so this will become this. Okay, so let's rewrite our equation here. So we have y c1 e raised to alpha x multiplied by cosine beta x plus I sine beta x plus c2 e raised to alpha x times cosine beta x minus, so this is already minus, so minus um, I sine beta x. Okay, so there we have it. Okay, let's just remove the parentheses here. Okay, so there you have it. No? So this is already a solution. So though we haven't removed the I completely yet, so that is what we're going to do in the next step. So in the next step, we are going to set different values for C1 and C2. For C1 and C2 right here. So these are arbitrary constants. So we can set any value that we prefer. So in this step, we will set C1 is equal to 1 and C2 be equal to 1. Okay, so let's do that, and at the same time let us distribute these. So y is equal to e raised to so this will be y is equal to e raised to alpha x multiplied by I mean cosine beta x, and then what we have here, uh, plus e raised to alpha x I sine beta x, and then plus e raised to alpha x cosine beta x again, minus e raised to alpha x I sine beta x. So as you can see here, these two will be cancelled out. Okay, so then we are then left with y is equal to 2e to alpha 2 alpha x 2e raised to alpha x cosine beta x. Okay, so this is really nice. So we remove the I here, right? Okay, so if we do that, so if we do that again to the same equation, and we let C1 is equal to -1 and C2 is equal to, C1 is equal to 1 and C2 is equal to -1, then we will get another version of this, which is equal to 2e raised to alpha x I sine beta x. Okay? So you can do that as an exercise. You distribute it right here. So this will be the result that you will get. Okay, as you can see here, we have two solutions here, right? We have two solutions, and for y2 we still have an I here, right? Okay, so if we recall the corollary, the first corollary of the superposition principle for homogeneous equations, it says that if y1 is a solution, then c1 times y1 is also a solution, right? So if we apply that here, then we know that these two right here, y1 and y2 are solutions, and therefore y1 is equal to c1 times 2 e raised to alpha x cosine beta x is also a solution, right? And y2 is equal to c2 2i e raised to alpha x sine beta x sine beta x is also a solution. Okay, and c here c here is not limited to real numbers, so you can also have a constant that is complex. So we can rewrite this as y1 is equal to c e raised to alpha x cosine beta x, and y2 is equal to let's say c1. So this can be, let's set this as c1, and then let's set this as c2. So you get c2 e raised to alpha x sine beta x. Okay, so therefore, since these two are linearly independent, so we can write our general solution to be y is equal to c1 e raised to alpha x cosine beta x plus c2 e raised to alpha x sine beta x. Okay, so this is our result. So if we get a auxiliary equation with complex and conjugate roots, then this will be the format of our general solution. Okay, so we will apply this in the next video, and thanks for watching this video. See you in the next one.